let's say that we have this road right here. It's a 2D number array and it's called just road. And let's say we have a car and the car starts at this point and it wants to get to this point right here. So we want to get from start to the end and we want to find the shortest path that we can take to get from the start to the end. Now, just seeing this with the naked eye, it's pretty obvious. We can probably go all the way up and then we can just take a right and go here. Or we can go to the right and then go up. That would be a shortest path too. Now, what we definitely don't want to do is go right and then just go up one and go all the way left and up one, then all the way right. If we go in a zigzag pattern, that is clearly not the shortest path. So some are shortest and some are not. And if there are multiple shortest paths, then we just want to return any one of them. And that's fine. Now, what we also want to do is ensure that we don't revisit a place that we've already been on. So when the car drives, it shouldn't go, if the car goes to the right like that, it's not allowed to go back to a square that it's already been on. So we cannot revisit places we've already been on. The car cannot go diagonally as well. Only up, down, left, and right. Now, given these conditions, we want to write an algorithm that'll take in a road along with a start position and an end position, and then return the shortest path that it can take. So let's go ahead and get started, and let's go ahead and do this. So if I were to write a function, and I'm going to call this get shortest path, and I'm going to have this take in a road, a start, and an end position. That's what we want to do. And I want to return a collection of coordinates where each coordinate specifies one of the squares that the car goes in order to get from start to the end. So that's that. So let's go ahead and do that. And we're going to call this collection shortest path. So, and I want to just return that right away. We're going to develop this algorithm methodically. So let's go ahead and do a console log here and see what it looks like so far. I mean, nothing much has been done here, but I want to make sure we're all good. So road, and I'll take in a start position just for simplicity. We'll go at the bottom left corner. That's where we're starting. And we're going to go to the top right corner. So the bottom left corner is row indexed at 2. This is all 0 base. So row 0, row 1, row 2. Row 2, column 0. That's what that is. So it'll be 2, 0. And then the end position would just be row 0, column 2. Just like that. So that's that. So let's go ahead and run the code and let's see what we have. So far, so good. We just have an empty array. Okay. Now is where the real work begins. So if I'm on this starting point right here, I want to first identify where can I go next. Now, if I'm there, I can either go above 1 or I can go to the right 1. That's if I'm right here at the bottom left corner. If I were right here in the middle, then I have 4 places that I can go, up, down, left, or right. So depending on where I am, I want to identify where are the immediate next spots that I can go to. And that allows me to start traversing or start driving in this case. So how about we write a function that will take in a point. We'll call this get valid moves. What it'll do is it'll take in a location along with the road, of course, and it'll return all of the valid moves, the next immediate moves of that location. So what we're going to do is we want to actually we want to spell this out. So I can either go to the left, right? And if I go to the left, what does that mean? Well, of course, I can go to the left here if I'm at the bottom left corner, but let's say I were here. If I go to the left, what that means is I decrement the column by 1, but I keep the row the same. So decrementing the column by 1, but keeping the row the same means I want to access the row in location. So the row is the same right now. What I'm doing here is I'm just creating coordinates. The same way we're given right here. We're just going to create coordinates of where we want to go. So if I were to decrement the column by 1, it's just like that. And now if I want to go to the right, well, it's the opposite. I want to increment the column by 1, but still keep the row the same. So let's go ahead and do that as well. Just going to take this, copy this, and call this right. And I just want to increment like that. Okay, now if I want to go up, then that is decrementing the row by 1, but keeping the column the same. So let's go ahead and do that. And now, if I want to go down, same deal. It is incrementing the column. Sorry, the row by 1, keeping the column the same, just like that. So now we have our 4 directions, but as we have pointed out before, sometimes you cannot go in all 4 directions. If you're on the edge of the board, for example, you cannot go on all 4 directions. So we want to find a way to filter out all of these for just the valid moves that we can go on. These are the possible moves. Now let's go and reduce it down to the valid moves. And an easy way to do this is we're just going to throw this all into an array called left, right, up, down, like that. Throw it all into an array. And I want to just use the filter function because I'm filtering this out. I'm filtering out each move. And I want to make sure each move satisfies some conditions. And this is what we're going to do to check whether we have road remaining to go to where we want to go. First thing is we want to ensure that the column that we're about to go to does not fall below 0. So if we're here, we don't want to go below that because we can't. Same thing for the row. The row should not fall below 0 as well. So let's go ahead and do that. So if the row, I want to make sure that the move of the row is greater than or equal to 0 at all times. And also, the column that we're about to go on, or we're planning to go on, should be also greater than or equal to 0, like that. Moreover, I want to make sure that the row, once again, that we're planning on going to is less than the rows. So, for example, if I'm here, I cannot go down because there's no road left. So I want to make sure it's less than the rows. And same deal, I want to make sure that the column that I'm about to go on is less than the rows columns. So let's go ahead and do that. Okay, so now we have our 4 directions that we can go on. And let's go ahead and actually test this out. So what I'm going to do is same deal as I've done last time. I'm just going to console log this right now. I'm going to call this get valid moves. We're going to have it take in our starting position, that is row 2, column 0. Give it a road so it knows what to work with here. And we're going to just run this code and see here we have 2 positions. We have 2, 1 and 1, 0. So if we're starting here, we can either go to 2, 1, that is row 2, column 1, that is this place right here, or this place right here, that is 1, 0. Now, just to do one more test, I'm going to give it this middle position right here, and I want it to return 4 possible moves. So that middle position is just 1, 1, like that. Okay, so if I were to just give it 1, 1, I were to put it in proper syntax. So just like that. Give it 1, 1, and then just run it, and now I see 4 moves. And these are the 4 moves. That's just up, down, left, and right if I'm right here. So far, so good. Okay, so let's go ahead and take this out. And I'm going to go back to testing this code right here, our get shortest path function. So now, once we've identified all of the next moves of a position, we're not done because that's just one move. Then, for each of those next moves, I want to identify those next moves. In other words, once I'm here, I want to identify the next move, which is here and here, like that. And of course, a next move of this 0 that I'm highlighting right here can also be this 0 here. But again, we've already visited that 0. We cannot revisit that 0 for a given path. So we're going to deal with all this stuff. But first of all, how is it that we can go from one valid move to all of its valid moves to all of its valid moves until we reach the end? It sounds to me like a sort of recursion. So let's go ahead and do that. We can even do it in an iterative fashion, but recursion to me sounds more intuitive. Just the way I described it. So let's go ahead and do that. So I want to create a function, and I want to call this traverse because that's what we're doing. We're just traversing. And in this traversal, I want to know where I'm starting from. I want to know where I'm ending. I want to know the road that I'm on. Not just that, I want to know the current path that I'm building. So for example, if I start right here and I go here, and then I go here, and then I go here, and so on, that is one path that I'm building. I can go somewhere else and build another path. So all the while I'm doing this traversal, I am building out at any given moment a current path. I'll just call this current path, like that. Now, of course, we can have many current paths, but the point here is to get the shortest path. So what this traversal should also take in is a shortest path. Because at any given moment, what I'm going to do is when I reach the end, I'm going to compare. Is the current path that I just built, is that shorter than the shortest path that we've seen so far? If so, then update the shortest path. And you'll see all this logic shortly, but I just want to define the function signature. So I'm going to put in shortest path, just like that. Okay, one more thing. We're almost done here. We also need, remember, we don't want to recheck or revisit places that we've already been on. So if I'm here and I go up here, I cannot come back down here. For a given path, that is, I cannot come back down here. So I want to see some way of capturing places that I've already visited. And we can do this in a number of ways. We can do it with an array, a JavaScript object, a map. But for semantics and for clarity, I want to use a set right here. So let's go ahead and first define our function signature here. So we have all this. This is our function signature. All right, that's that. Now we have to obviously call this function. So let's go ahead and call this function. So if I were to just say traverse, open this up, give it a start, give it the end, the road, and the current path that I'm building, well, it just starts off as empty because right now as it stands in the beginning, there is no current path. So we just give it empty, an empty array like that. We also want to give it the shortest path. And the reason I've created this shortest path is to pass it in here. Why am I doing that? Because the entire time this traversal is operating, it is updating and editing this shortest path as necessary. Now you might notice this function is not a pure function because once again, it updates, it mutates inputs that it's given outside it. So it's not a pure function. So we can talk about pure functions and all that later, but I just want to point out that this is not a pure function, but the point of this video is to generate a shortest path algorithm from scratch. So that's that. I just want to point out certain things that are happening here. Okay, we have the shortest path, and we also, remember, we talked about a visited set. So let's give it a set. Let's call it visited. Just like that. And I want to just throw in visited right there. So there we go. And now we see my traversal, and now we see the shortest path. It is returning the shortest path after it has been operated on by the traversal. That's that. So this function is good to go, but of course traverse now has to be filled out. So let's fill it out. The first thing we want to do is we get the start position. Given whatever we're starting from, we want to get that position's valid moves. That's the whole point. That's why we wrote this right here. So I want to say something like valid moves, and I'll say get valid moves of the start that I'm on, and it needs a road as well, just like that. And then for every valid move, I want to get those valid moves. In other words, I want to recall this traverse. That's the point of the recursion that we're writing. So for each move, I want to traverse. Let's just traverse right away. And we're going to obviously add more logic shortly, but for now, let's fill out the bare bones details. So I want to see where I am starting from. So do I pass in start here, or do I want to pass in move right here? I want to pass in move right here, because for every new move, that becomes the starting position. So if I'm starting here, and then the next moves are here, and I decide to go here next, well then I want to find this move's next moves. this then becomes the start, and so on. That's why I was saying it's a recursion. It's recursive in nature. It's a subproblem with subproblems and subproblems. Hope that makes sense. So, okay, we have the move here. We have an end position. That's the end. That stays constant every time. We know where we're ending. We have a road. And now we want to pass in our current path. So we have to start building our current path. So as we generate, as we get moves, we have to push in to our current path the move that we have, just like that. Because as I generate this move, I'm building out my path. So I want to push it in as a collection of coordinates, right? So push in this coordinate, then push in this coordinate, and so on. Pushing all of the moves that the current path is having at the moment. So just do current path like that. And then I also want to pass in the shortest path. And shortest path we will update not here, but shortly somewhere else, you'll see. And we also want to take in the visited. Well, where is visit? What's happening with the visited right here? Okay, so as soon as I come on a traversal, as soon as I invoke this traversal function, would it not make sense to say that as soon as you land on a spot, you've already visited that spot? It's right. So as soon as I land on a spot, in other words, as soon as I call this traverse, because remember, traverse is called for every spot. So as soon as I land on a spot, I've already visited that. So what I want to do is also mark what I've seen just now inside. I want to add it into my visited. Now this is something to be careful about. So I have this set here, and I've just added in this start here. And keep in mind, start is a array like this, 1, 2. Now this set will ensure, if I add another start in, it's supposed to ensure that it only has unique values. However, if I add an array like this, and I were to compare this array, if I were to add another of the same arrays, this set treats these two actually as different values. And that's just a JavaScript caveat. We don't have to talk too much about that, but I want to point this out here because this would lead to unexpected bugs. If you thought the set was going to do a deep comparison of the arrays and make sure they're the same, that's not what it does. It's more of a shallow. So I don't want to work with such nested type of objects or objects where I can get these value reference type of errors. I want to just work with something simple and primitive. So what I want to do is just fetch the string version of the start. So the string version is just 1, 2 in a string like that. And I do join to get that. So this way, if I were to add another one of these strings again, this set would know right away. You've already added that and it's not going to add another. This is just another JavaScript caveat. So I want to just have you aware of certain things like that. So that's that. So we have visited the place that we are starting from. And every time we start from somewhere new. So that's that. Okay. And now we have added it to our path. And now we are traversing. And now we want to know at what point do we stop traversing? Because if we don't define that, we're going to end up in an infinite loop. So let's go ahead and define that right now. So I want to say if the start that I'm on, not just that, remember, I want to join this. I want to see if the string version of the start that I'm on equals to the string version of the end that I'm on. So just like that. At this point, I want to stop my traversal. I'm just going to return this right here. So none of this stuff is going to fire if we are at the end position right here. And it's also at this point that I want to update. I want to update my shortest path. And in fact, we'll go ahead and do this. But for now, I'm just going to mark it as a comment, and we're going to get to this shortly. Okay, so we have this. We have this. Okay, one more thing I want to say, which is once you add in the current path, note here, if I'm here and I'm right here and I keep adding in, right? I keep pushing into current path. I pushed in one more, and I pushed in one more. Now I've reached the end. Okay, let's start comparing and so on. Now, this is not the only path that I can take. So I've pushed in this, but a next move of the previous 0 was also here. So I could have just as easily gone all the way down like that. So I still have to check for that. In other words, I've just gone one path. Okay. But once that recursion is done, we have to now check for another path. In other words, we have to make room for another possible next move. We've already pushed in all this stuff right here, but once the traversal is done, I want to pop off. I want to pop off the latest next move that I added into my current path to check for the next one. This might be a little confusing, but as you write more recursions and you sort of get the hang of stacks and popping off stacks, this will make a lot more sense. So what I want to do is actually, once I've finished looking and updating the current path that I'm on, I want to actually pop off of just the last element of my current path. Again, the reason I'm doing this is to make room for the next possible move that I can look at. And this, by the way, happens every single step along the way. Because it's a recursion, it happens even here too. So even here, when I'm right here, I don't have to always go here. I could also go here, right? There's just several sort of conditions. There are several outcomes that I can have, and I want to make way for that. So I want to pop this right here. Now, not just that. Remember, we want to make sure we don't recheck a place that we've already been on, but this only applies to the current path that we are on. In other words, if I go from here all the way to here, now, of course, I cannot go back here. And if I go, so I keep going up then, let's say, I go here, and I cannot go back here, right here. I cannot go back here. I cannot revisit places I've been on for the current path. That doesn't mean that I cannot ever revisit a place. Because, for example, there could be other paths that I can take that require for me to go on squares that I've been on already, go on points in the road that I've already been on. So the whole point of visited is to ensure that only for a current path, for a path that I'm building, I don't revisit that. So just the way we pop off here, what we also want to do is once we've fully traversed for one possible path, we want to make way and clear that from the visited for our next possible paths. And what I'll do here is I'm going to do a delete. I'm going to remove from the visited set what we just added in. We just added in the start. I'm going to remove that as well. This clears the way as well. Okay, so this part looks good so far. Let's go ahead and get to the meat of this, which is the updating of the shortest path. Okay, when do I want to update my shortest path? Shortest path starts off as empty. So I want to only update it if there's something in the shortest path. If the shortest path has something in it, then and only then I can compare that with my current path. So let's go ahead and do that. So let's say if the shortest path dot length is greater than 0, all I'm saying here is, does it have something in it? And okay, if it has something in it, then if the current path that I'm on, if that is less than, right? If it's shorter than the current shortest path that I've built up, then and only then we want to update the shortest path. And now I'm going to take this update here and I'm going to just fill it in right here. And we're going to get to this shortly, I promise. But we're going to now see, okay, this is only if the shortest path has something in it. But we know that the shortest path starts off as empty. So we want to do an else here to catch that case as well, if the shortest path is empty. And if the shortest path is empty, then what we want to do is push into our shortest path. Now, what is it that we want to push? So I'm going to do something like this, shortest path, push, and I want to push in just a copy of the current path that we are on. This whole destructuring thing is more of a JavaScript syntax, but all I'm doing here is creating a copy of the current path. The reason I'm creating a copy, once again, is I am mutating current path right here, and I don't want to again get into bugs related to working with references versus copies. So just to keep it simple, we're going to push in a copy just like that. What I've effectively done here is I've said the shortest path, put inside it the current path that we are on. That's it. This also allows me to store the current path that I'm on. This is the current path so far. Okay, Now, if we have to update the shortest path, what we first want to do is take whatever was in shortest path and pop it. I want the shortest path to only have one element at all times, because we're only storing one path at all times. This is for optimality purposes as well. It's for simplicity as well. But basically, I don't want to store every possible path. I want to only store one. This way, I can just store what I need to store. That's it. So pop that off and then update it as usual, just like that. So here, what has been done here? I'm saying if we've reached the end, if shortest path has something in it, and the current path that we've built up is less than what we have, then update what we have. Update our shortest path. Otherwise, if the shortest path has nothing in it, well then just whatever current path we just built, put that inside shortest path, just like that. So the shortest path is a holder of the current shortest path. That's what that is. And because it holds the current shortest path, actually, there's actually a little bug here, if you've noticed. So I'm comparing the current path's length to the shortest path length. But the shortest path is actually extra nested. It is not just a 2D array, it is actually an array of arrays, because notice we are pushing in a 2D array right here. So what I want to do is access the 0th element from that. That's it. Shortest path, once again, is a holder of the shortest path. In fact, what might be a more apt name is shortest path holder. That's neither here nor there. So that's that. And because shortest path is a holder, I want to return its first position, 0th element, that is, just like that. So that's that. So this algorithm here should do it. It should do the trick. So let's see what happens. It's quite a bit of code we wrote, but again, let's see what happens. So I'm going to invoke the shortest path from the bottom left corner, top right corner. Let's see what happens. Okay, we have a bug. Let's go ahead and deal with that. So here we see get valid moves. Oh, okay, max call stack exceeded. Perfect. So this is actually, I'm glad we got this bug. So go right here. Okay, we see valid moves. And what's the point of having visited if we're not going to use it? We're just adding stuff into visited. We're deleting stuff from visited, but we have to actually use visited. The whole point of visited was to ensure that we don't traverse if we've already visited. Now we are going in an infinite loop. That's what we are doing right now. Because what we're doing is we're going to this 0, then we're going to this 0, then we're going back to this 0, then we're going back to this 0. We're just in an infinite loop right now. So even though I have this condition to stop at the end, I'm never getting to the end because I'm never I'm never avoiding traversing when something's already visited. So let's go ahead and use our visited. All I'm going to say here is if the visited that we have has the current move, and I'm going to join this again. Remember, we're dealing with strings here. If it has what I've already seen, if I've already seen it, I just want to return right here. Return, because I'm in a for each function, return means obviously this stuff right here does not get called and it goes to the next invocation. So none of that should be invoked and it should be good to go now. Let's go ahead and check this out. Okay, perfect. So look at this. We have gotten a path and let's make sure this is correct. So if we start from 2, 0, that is this right here, and then we go to 2, 1. 2, 1 is this right here. That is row 2, column 1. Then we go to 2, 2. And then we go to 1, 2. Then we go to 0, 2. So what we've done is we've gone all the way to the right and then we've gone all the way above. And that is a shortest path. There are other shortest paths, but this is a shortest path. That's good. So we got it working. So now I want to show you something. I want to show you just how quickly this algorithm could get a little out of hand, because algorithms like this, the shortest path algorithm, they're not necessarily efficient, if you want to call it, because if I double the size of the road from a 3x3 to a 6x6, remember, I'm checking all possible paths here. Even though I'm only storing one path, I still have to check all possible paths. When given to a computer program, I can't just eyeball it and say, okay, I'm going to go all the way up and then I'm going to go to the right. So I'll show you what happens here. So give it a row 2, right? And given row 2 and row 2's bottom left corner would be 0, would be 5, 0. Its top right corner will be 0, 5. Let's just see. This will take a few seconds to run. So, okay, so the first one's already run. We see our answer here. And now we're going to wait for the second one to run. It should come any second now. But as you can see, it is taking some seconds. So, okay. So what do we have here? We have a few things. We start at 5. We start at 5, 0. We go to 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 4, 5, 3, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what I've just, you see here, to get from the start to the end, we need 10 steps, and we have 1, 2, 3, 4, 5. We have 10 steps here. So it's just another shortest path that we go on. So that's that. So I hope this algorithm makes sense. We've written a lot of code here from start to finish. It's not a trivial algorithm. So yeah, we also covered some caveats like dealing with references and values, and that's why we have join here and using visited sets. We also talked about pure functions, so we covered a few things. This is obviously an impure function, so that's that.